Hi, this is Online Class 18. We're going to cover section 10.2 today called Correlation, Friday, December 7th, Fall 2012, and my name is Carl Perez, Math 125 at SUNY Cobleskill. Alright, correlation. I'm sure you've heard the word correlation many times before, and what we want to do is open up a new chapter. Chapter 10 is entitled Correlation and Regression. Well, first correlation, and then we're going to talk about regression in our last face-to-face class on Monday. Alright, what I want to look at here is, let's say someone tracks the cost of a slice of pizza in New York City versus the sub-cost of the subway fare. And what I'm going to do, try to make this as nice as I can, drawing freehand here. And what we're going to do is survey these prices at different years in the decades. Let's say in 1960, the cost of a slice of pizza was 15 cents and the Subway was also 15 cents. Alright, let's say in 1973, we run the same survey, and the cost of pizza is 35 cents. And the subway fare is also 35 cents. Let's say we run the same survey in 1986. And the cost of pizza is $1 in New York City, and the subway fare is also $1. We go to 1995, and the cost of pizza is $1.25, and the subway fare is now $1.35. Let's go up to 2002, and the cost of pizza is now $1.75 per slice, and the cost of a subway fare is $1.50. And we then go on to 2003, and the cost of a slice of pizza is $2, and subway fare is also $2. Oh, by the way, I was just in New York, and the cost of a subway fare was $2.25. That was for a one-way trip. And so could it be the price of the subway has gone up only a quarter in 9 years? That's kind of hard to believe. Alright. Yep. In trouble again. Alright, here we go. Alright. So, of course, you're wondering about the relationship between these two variables, pizza and subway, and it appears there's a pretty direct relation. Formally, a little more formally, I'm going to ask you this question. Is there a correlation between the subway prices and the pizza prices? And of course, we might suggest a very strong yes to this to answer this question. Well, we're going to sharpen up that idea of a correlation and learn today how to actually assign a number to the degree of correlation between variables. That's what today's lecture is all about. Hang on a minute. Alright. The textbook definition says something like this. A correlation exists between two variables when the values of one variable are associated with values of the other. Okay? And again, this is basically from the text, and they're somewhat vague with this idea of associated. Well, the idea is there's different types of correlations. We're only going to be talking about linear correlations in this course. So when you see associated, I guess we can assume in our minds anyway that we are talking about being linearly associated. All right? What do I mean by linear associated? Well, if we look at a scatter plot, which we can do on our calculators, I'll show you how to do that in our next face-to-face class, of the pizza and Subway data. Well, we'll get a picture that looks something like this. I'll do my best to scan this by hand. If we're going to track the value or the cost of a pizza slice versus the cost of a Subway fare, let's see, we start out near zero and end up at $2. So I'll let the x-axis be dollars of pizza cost, and let the y-axis be the cost of the Subway fare. Well, we can see, when pizza is 15 cents, the Subway is 15 cents. When the pizza is 35 cents, the Subway is 35 cents. When the pizza is $1, the Subway is $1. All right, and we can keep plotting this. Let's see. When the pizza is $1.25, the Subway is $1.35. So we jump up a little bit. When the pizza is when the pizza is $1.75, the Subway is $1.50. Right, so pizza is $1.75, maybe something like that. I may be exaggerating a bit for demonstration purposes. When pizza is $2, Subway is $2. All right, so we can see as we graph the bivariate or the two variable data here, we can see a kind of linear relationship is suggested between these two variables. All right, so again, I'm going to suggest here that this data indicates a strong positive correlation or a strong positive linear correlation. All right, well, the idea, what does positive correlation mean? Well, you can probably figure that out on your own. Let me make that a little more formal. If we're talking about a positive correlation, all that means is as x increases, then y increases. So in other words, if your pizza price is going up, if as a result your Subway fare also goes up, well, then you're talking about a positive correlation. Well, that suggests there's something called a negative correlation. And of course there is. And as you might suspect, in a negative correlation, as x increases, then y decreases, as you might suspect, and of course vice versa. Right? A negative correlation would of course look something like that in terms of a scatter plot. And there's also a case, of course, where there's no correlation exists, neither positive nor negative. No correlation. Yeah, in that case, there's no predictable pattern, and your scatter plot might look something like this. No discernible increase or decrease in one variable or the other as you scan through their possible values. Okay. Alright, of course the textbook does a better job of these. You can see the graphs in your textbook on page 519. Alright, now I want to get back to this idea of how to measure linear correlation. We can actually stick a number onto this to define just how strong it is, positive or negative, in a numerical sense. Right? How to measure strength of correlation. Well, we're going to talk about something called the linear correlation coefficient, which we're going to label with the small letter r, right? Lowercase letter r. Sometimes this is called the Pearson linear correlation coefficient to honor the man Pearson that invented this. Alright, this is established via a formula. And it's a terrible formula to do by hand. See formula 10.1. See formula 10-1 on page 520 if you're interested in the anguish that the calculator is going to save us from. Alright, calculator does this. The long and short of it is, if you look at the formula long enough, you can justify this statement that R, the linear correlation coefficient, is always between 1 or minus 1. Alright, so I can draw a very simple, I'm going to call it R graph, indicating minus 1 and 1 and everything in between. Alright, what we're going to do is once we compute R values, we're going to establish what we call critical values for R. And if I'm in this range between the critical value and R, I'm going to claim there is a strong positive correlation. Okay? If I'm in this range between my critical value and -1, my left critical value and -1, of course I'm going to claim there is a strong negative correlation. And if I'm between the positive and negative critical values, which I will establish later, I'm going to claim there's no correlation or no significant correlation as derived from the data. Right? So let me write that down a little more formally. If R is near 1, implies strong positive correlation. If R is near -1, strong negative correlation. And if neither near 1 nor -1, we claim there's no significant correlation. Alright. Alright, so how do we find this mysterious R value? Well, of course, we're going to use our calculator. Alright, we're going to compute the linear correlation coefficient R for the pizza Subway data. Alright, so get your calculators out and we'll run through it here. Well, basically we have to enter in our data, our bivariate data, our two-dimensional data. Right? Every pizza value has a associated or corresponding Subway data. So we got to enter in these data values in lists. Alright, well, the first thing you have to do is clear out all the old data. So on your calculator, hit Stat, Edit, clear all data from L1 and L2. We're going to be using list L1 and L2. And as you might suspect, we're going to enter the pizza values, the pizza cost values in list L1, and of course then the Subway values in list L sub 2. Alright, once you've cleared out the old data and entered the new data, then it's kind of a breeze. Hit Stat, then Calc, then this function lin reg ax plus b, and press Enter twice. You press enter once to call up the command to your home screen, and then enter again to execute the command. Alright, the following values should be displayed. And right now we're going to be interested only in R. Alright, so on the calculator screen you'll see y equals, don't worry about it, you'll see a equals, you should see b equals, you should see r squared equals. Ignore all those values for now. We'll talk more about these in the face-to-face class on Monday. Here's the r value. Was it 1, 2, 3, 4, fifth on the list? 0.988. Alright, this is our linear correlation coefficient. That's a 9 there. Alright, so clearly my R value is near 1. And as we might expect, just from glancing at the data and from a glance of the scatter plot, a strong positive linear correlation, which we'll just call correlation in this section, is suggested by the sample data. Okay? Alright, if R is not displayed, I'll talk about that at the end of the lecture. It could be that your calculator is not displaying R. Don't panic. This is a small fix. Might as well talk about that now. If your calculator does not display R, it's a small fix. Basically, you've got to hit at the second level, hit the catalog operator. It's above the numeral 0 on your calculator. Enter. Highlight catalog and hit enter, and scroll to a command called diagnostic on. And that's got to be turned on for the R value to appear when you hit linrig AX plus B. Right. Hit enter twice. And with that result, you should be ready to go and try again, and you should see R nicely. Okay? Alright. Alright, let me get a fresh screen here. Now that we know how to calculate R, I want to talk a little bit about this. How near 1 do we have to be to establish a strong positive or even strong negative linear correlation? Let me get a new screen here. Alright. Alright. Let me start out with this. How to determine critical values. Critical values for R. And basically, I'm in this kind of situation, tracking my R values. I want to establish cutoff points. I'm going to have a left critical value and a right critical value. Beyond this critical value, between the positive critical value and 1, we're going to claim a strong positive correlation, and of course a strong negative correlation down here. In between, there's no correlation, as we talked about before. Alright, what I want you to do is see table A6. on page 760 in Appendix A. So please turn there now. And we're going to learn how to establish these critical values. In other words, at what level do our R values become statistically significant? Alright, you'll see the table A6, let me turn there myself, on page 760, entitled Critical Values of the Pearson Correlation Coefficient R. Alright, you'll see an N column, an alpha equals 0.05 column, and an alpha equals 0.01 column. Alright, like our earlier work in hypothesis testing, your level of alpha determines how statistically significant you're going to set the bar at. In other words, what's the burden of proof here to claim a positive or negative correlation? Alright, for the pizza, let's see, N, let's talk about N. N is going to be your number of pairs of data. Since your data is two-dimensional here, you're entering your data in pairwise. For the pizza subway data, our N was, of course, 6. Alright, our alpha, I'm going to pick alpha equals 0.05. So all you simply do is look at the intersection in that table of the N equals 6 row and the alpha equals 0.05 column, and I get a critical value of 0.811. Right, now that only gives us a positive critical value. If you read the fine print at the bottom of the table, it says, well, note that we're talking about the absolute value of R being greater than the critical value in this table. Informally, we take the positive and negative of that critical value in that table. Okay? Alright, so once I establish my positive and negative critical values, then I can make a nice little graph here. My positive critical value is 0.811. My negative critical value is going to be negative 0.811, and that establishes the level of proof I will need to establish a statistically significant linear correlation, positive or negative. Alright, recall R in this Subway pizza data was 0.988. And what I'm going to do is draw a verdict arrow. I'm going to call this a verdict arrow showing me I'm clearly in what I call this critical region for R. And based on this, I'll say our data suggests that there is a strong positive correlation between pizza cost and subway cost through the years we studied at alpha equals 0.05, or really this number is so close to 1 I probably would have claimed a positive correlation at any reasonable choice of alpha. Okay? Alright, let's work out another exercise before we call it a day. I'm going to say, well, let's look at exercise 15 on page 532. Let me turn there myself. Alright, talks about blood pressure measurements. And I want you to turn there and familiarize yourself with the data and the problem statement before we go on. Please pause now and turn. Alright, it tells us blood pressure measurements listed below are systolic blood pressure measurements in milligrams of mercury obtained from the same woman based on data, etc. or let's see, let me read the title of the journal article. Consistency of blood pressure differences between the right and left arms, etc. Alright, so basically they're listing all these blood pressure measurements, one set taken on the right arm, one set taken on the left arm of different patients, right? And they ask, is there sufficient evidence to conclude there is a linear correlation between left and right arm systolic blood pressure measurements? Alright, let me take a minute to copy this data down here. It'll only take a second. Alright, so these columns indicate, of course, the same patient with blood pressure measurements taken in different arms. Okay, so 144 there. Alright, well, looking at this data, I can't really tell. Sometimes you can kind of guess whether there's going to be a correlation or not. Right there, I can't really tell by glancing at this data whether or not there's going to be a correlation, positive or negative. Alright, well, that's where R comes in, right? So step one, find R. Alright, so go through the previous process, take out the old data, put in the new data, go to linreg AX plus B, and I can establish easily from data an R value of 0.867. Okay? Step 2, determine critical values. For R. Well, again, I'm going to use the textbook tells us in this set of problems to always use an alpha of 0.05. And again, that's kind of a middle of the road value. Again, we'll use table A-6 on page, let's see, what page was it on? Table A. 6 on page 760, okay, to establish those critical values. We've got 5 pairs of data here, so n equals 5. Alpha equals 0.05, so if I look at the intersection of that row and that column, I get a critical value, a positive critical value of 0.878. And again, to establish a high and low critical value, I simply take plus and minus 0.878. I'll draw my little R graph, and I'll expect you to do this on test day. My left critical value is minus 0.878. My positive critical R value is positive 0.878. And I've lost sight of R. Let me write it down here again. R from this data was 0.867. So I'll launch my verdict arrow into my diagram, and you'll see we fall short, maybe exaggerating this a bit, but certainly falls short of the critical region established by plus and minus 0.878. Oh yes, I forgot. Please label these critical values on test day, and also label the verdict arrow, and make a clear showing of where you land in this diagram. Alright, so no strong positive correlation is suggested, no strong negative correlation is suggested. So from this data, you write this down. I'll say the data suggests no significant linear correlation. No significant linear correlation. Again, that's at alpha equals 0.05. level of significance. All right. All right. Let me read you what the instructor's manual says regarding this problem. Number 15 claims there is not sufficient evidence to support the claim of a linear correlation between the systolic blood pressure measurements of the right and left arm. And that's kind of what we perhaps saw at first glance of the data. Alright, so please be sure to work out your homework problems and get a list of problems very similar to this. Note in the text that they say use alpha equals 0.05 for all the problems I'm going to give you in the homework set. And I guess that's it. Okay, we're hitting about the 31-minute points. We'll call it a day. This concludes Online Class 18, Section 10.2. That is all.